Thank you. So we have seen this morning very beautiful demonstrations of cooperative behavior in acto-myosin systems. I will be talking also about acto-myosin system, but a special one, and as I would think the simplest possible one. So obviously it lacks a lot of properties of generic system, but the advantage is that you can go quite far in making it transparent. So this is ongoing work with the PhD students, Matthew Carroll and Roman Sheshka, done in École Polytechnique. Something has been this. Yeah, I think he tried to make automatic running, but disabled probably. So it doesn't follow my controls. Sorry about this.
Is the tech help person in the room?
I'll try again. Ah, yeah. Okay, it works. All right. So we have seen this morning the complexity associated with multiple actin filaments interacting with molecular motors and different cross-linkers. So geometrical complexity of the system is enormous. Now, what is the simplest system of this type? Probably sarcomeric system that we observe in skeletal muscles. So this system is practically a crystal. On the side it looks like hexagonal crystal, and it consists of fibers, but fibers are highly organized. So here we see the actin fibers that are analogs of these pink ones, and then we see myosin fibers that have these appendages that are shown here in green, and that are responsible, that are actually motors. So this system has many features of the more general system. For instance, it has passive cross-linkers. You see here the contraction process shown. We see different type of passive cross-linkers that ensure the crystal structure. However, it's not rigid enough, so it's below the staticity level here in terms of the number of nearest neighbors, so those fibers can easily go. But we have also active cross-linkers, and we have motors. Now, of course, the system is also rather complex. So we'll go even further. We'll study passive behavior of this system. Passive, so it's a kind of a boring system. So what does mean passive? It's known that when, for instance, loads are applied to the system at very small time scales of, say, 1 millisecond, it exhibits a certain type of elasticity, and that's associated with passive behavior. So what is involved here is folding and unfolding of attached cross bridges. So if you want, it's a power stroke, but without power. So we have here bistable elements that can be in two different configurations. And so the system, for instance, when it's shortened, it recovers partially the drop of stress by folding those elements. And that's the mechanism of fast recovery that doesn't require ATP activity. and also similar things when those elements unfold when you suddenly stretch. So this folding and unfolding has the, in this muscle language, special terminology is used, power stroke. But here it's without power. By the end of the talk, we'll recover some of this power, but here we'll just treat it as a bistable element. So there were many claims that it's boring and it's just some kind of viscoelasticity. However, there were always some kind of unexpected features of the system, and I would list some of these features that at least attracted my attention to the system. There were reports that it exhibits negative stiffness, which is quite unusual for stable materials. Then another example is it looks like it shows it behaves differently in hard and soft device. I'm using here the terminology of mechanics. In muscle world, it would be called isometric and isotonic loading condition. Again, I'm talking about passive response. So this would also be strange for a material that has many elements, because those systems, even one single half sarcomer, so-called, has up to 300 units that can fold and unfold. So if it's not close to thermodynamic limit, it's still, there are lots of elements. And then finally, in the state of normal functionality of the system, which is so-called isometric contraction, the system exhibits large fluctuations both in space and time. So that suggests that maybe something strange is happening here. Now, this is an evidence of negative stiffness. So this is a paper of Andrew Huxley, and he has several papers with co-authors where he would insist that his prediction would be that there is a negative slope here. And I'm talking here not about a single element, I'm talking about many elements here. So it's a collective behavior. And also some other papers that are all using this idea. I will later explain what it really means. Then there is an...
So is that a measure? So this is...
I'm going to explain those pictures in full detail, how they are coming from, and yeah. So this is a fast response at fast times. So at slow times, for instance, if you apply suddenly the stress, at smaller time the response will be different, but at fast time it's expected to be this way. Now, also the rate of recovery, so-called in soft and hard device, how fast the system responds to, say, sudden application of load. This is the rate of this response, seem to be very different in so-called isometric recovery and isotonic recovery. So the isometric recovery have been known for a long time, and actually Huxley was focusing his theory on this regime, but more recently there are several papers which seem to be indicating that this type of viscoelastic response would be very different. Can be like 5 times more slow in the conditions which we would call hard device, which we would call soft device. So this is also strange for a material. Okay, so from what I'm going to say, some unexpected conclusions follow. First, negative stiffness is an equilibrium effect. Second, barriers in soft device are much larger than in a hard device in this system. There is ensemble non-equivalence, which means that ensemble with a fixed force and with a fixed displacement are different. And finally, muscle material behaves like a ferromagnet near the critical point. So I was thinking that this would be a provocation, but I'm very glad that we have this picture even on the board that Fred McIntosh, as if we have kind of interacted, but we didn't. However, also there is a difference, because I'm going to talk about system at finite temperature, so my connection to ferromagnet will be almost literal. It's not a magnet, but it will be a fixed temperature, while he was talking about it more metaphorically having in mind a thermal system. But in fact, the collective behavior, so in a sense, the message here that collective behavior is not necessarily related to violation of the detailed balance, so it may be an equilibrium effect in this system. Now, these first three items are rather unusual, but if we think a little bit where we have seen this, we may think about self-gravitating systems, where it's known, for instance, that specific heat can be negative, and that, for instance, canonical and microcanonical ensembles are different. And this, so what is a connection with self-gravitation system is the presence of long-range interactions. So the architecture of our network, in particular in the case of striated muscles, is such that long-range interactions dominate, and that would be a message. So this brings some kind of non-extensivity or non-additivity in the system, and that's it's an interesting feature that this passive behavior, seemingly boring behavior, already reveals. Now, the most interesting thing that we don't even need to invent a model. So there is a kind of a classical model in the field. This is a model of fast response by very distinguished people, in particular Sir Andrew Huxley. So this, in fact, all what I'm going to say will follow just directly from this model. And it's interesting that although it's a very highly cited paper, those features somehow remained unnoticed. All right, so what did Huxley and Simmons did? So they looked at the tetanized muscle, which means that there was an abundance of ATP, and then it was kept at a certain length, and suddenly this length was shortened. And then they measured tension. So first there was a drop of tension, which would be a behavior of elastic element, and then there would be recovery. And this is what we are interested. This is a recovery to a certain kind of quasi-equilibrium state, because it lasts for a while. And it lasts for as long as it takes time for ATP delivery limited process to start to work. So this is a fast mechanism, so that we didn't have a drop of force. But then there is a more slow process at tens and hundreds of milliseconds where already motors start to work. So it's commonly believed that at this range motors are not working, and this is a response of the and this is a passive or mechanical response.
And the active response, you eventually come back to T0.
Yes. You are in such a range of length where you can come back. So if you are overstretched, you cannot come back, or if you are too short. But this is a so-called plateau where you are coming back. So now those experiments have been since repeated in a hard and soft device. So Huxley worked exclusively in a hard device, which means he controlled the length. Since that time, people also controlled force. Now, then they would change the force, suddenly change the force, and again the system would recover, would exhibit some shortening, elastic shortening, and then another stage which bring it to this kind of quasi-stationary state at short time scales. Now, this is a collection of what is observed, this force that is recovered as a function of, for instance, this stretch. And in fact, the data on the final states achieved in soft and hard device basically agree. So here Z, those data are for hard device, this is for soft device, except for there is some little gap, near the state of isometric contraction where, for instance, in the soft device, you cannot get any points, you cannot reach any equilibrium. Here there is a place where large fluctuations are, and also the rates are very different. So this is a type of curve that where negative stiffness, Huxley suggests that there is a negative stiffness. In fact, here we have a behavior of many units, while negative stiffness would be associated with behavior of a single half sarcomer. So there is some kind of, there are paradoxes about this range, why it is, why rates are different.
Sorry, could I ask two stupid questions? The first one is, what should I be looking at in that picture that tells me that this has a negative stiffness? And secondly, if it has a negative stiffness, why is it stable?
This is experiment. In soft device, we don't have points. Here in hard device, we don't see negative stiffness, but here we're not seeing a single element. We are seeing many elements connected, say, in series. So as I'm going to say, there is there may be a reason why this negative stiffness disappears. But at least Huxley, to explain this picture, he used the as a property of an element negative stiffness. So we don't see here directly negative stiffness in this experiment.
You model it. The model contains
yeah.
negative stiffness. Okay.
Yeah. All right. So is it really viscoelasticity? So the first idea, actually, from the work of Hill, that there is some kind of simple element like this, consisting of springs and the dashpots, because that's the observed behavior, and that's what this element would show. However, if you look at the force as a function of applied stretch, so first you will have a kind of elastic, so suppose you shorten this system, first this spring would respond, you have elastic behavior, then at a longer time when this Kelvin type viscoelasticity would get into action, there would be a partial recovery, but again, then you will see the smaller stiffness of parallel connection of these two springs, but you will end up on this blue curve. While in fact, what is observed is that fast elastic response is like here, but then in a hard device, you would recover this level of tension, and in the soft device, you will recover this length. So you are on this curve rather than a straight line. So something more complex than this is taking place. Now, again, in the previous talk, we've seen this cycle. So this cycle basically is based on studying of acto-myosin system and solution, and it tells you the main players here. So in particular, this power stroke, which we view as just passive unfolding. So it's taking place here. As you see, myosin fibers have these appendages here, and the global heads here work as motors, but we neglect at the moment that they are motors. We just notice that they have two preferred conformational states. So we'll be focusing on this stage, which is much faster than other active stages, like we see 100 milliseconds, for instance. So we need to implement this unfolding into the model. Now we can model it very simply. So each head is a bistable element and a spring, because it has elasticity. So instead of this heel element, so we have a bistable element that can be modeled by piecewise quadratic energy, and there is a linear element that can be modeled by quadratic energy. Now, it's a bit tricky system because, for instance, if we control this y, the response is multivalued. That's clear because the forces in those two elements must be equal. So those two lines must intersect. They may have three intersections. And if we control y, you may have three values of x and three values of force. So at each length, this is a really at least bistable device. Now, here is a Huxley model. So the Huxley and Simmons model, which called HS, and surprisingly, it also works as a hard spin model because it's going to be a hard spin model. So they focused on one unit here, and it's a half sarcomer, and so there is an n units here, n elements, and n crosslinkers, in this case unfolding crosslinkers, and each one is modeled as a bistable element in a spring. Now, what they did is that instead of bistable potential, they just use a kind of a spin model. So it's infinitely deep wells. But of course, they didn't think about spins. They thought about chemical reactions, having in mind some kind of Kramer's ansatz here. So there are two states, and then there is a chemical reaction allowing you to change between these two states. However, there is also, you have to produce force, so there must be continuous variable here as well. So they, in this way, they essentially coupled this chemical reaction with the mechanical part, and then when the spring is stretched, it affects the structure of this potential. So it's like in a Bell's model for adhesive clusters, very similarly. Now, so that brings the interesting result that these chemical constants must be functions of the stretch of the spring. So they're no longer constants, they're functions. And here, we have a lot of freedom of modeling these functions. And while Huxley and Simmons were quite careful in linking those functions to really the action of the spring, afterwards, this approach that's called chemomechanical approach developed in the direction of really putting rather generic relation between generic functions here. They are related by detailed balance or control deviation from detailed balance, but since we have no information about barriers, it became a rather phenomenological fitting scheme. So we'll stay with the orthodox scheme where everything is kind of mechanical, and then we look at the energy of the system. So the energy of the system depends on states of individual units. So individual units here, spins, have two values, 0 and -1. So if x1 is -1, the value of energy is 0. If x1 is 0, then the value is V naught of the energy. So we try to keep close to Huxley language, so that's why it's unusual definition of spins. Now there is also elastic element here that's shown here. It's quadratic, and Z is our controlling parameter, the total length. Now this isn't a hard device, and it's clear that this is a sum of non-interacting spins. So it's a kind of a paramagnetic system. However, if we make a mild modification and consider force, controlled force rather than length, which was not in the original paper, we just have to modify our energy by adding this linear term. But when we add this linear term, now Z is no longer a controlling parameter. It's something that it's another internal variable, macroscopic internal variable. So obviously there will be smaller diffusion, faster diffusion for this macroscopic variable. So if we adiabatically eliminate it, then we'll see that the energy depends on sum of xi squared. And this is already a mean field interaction. So that means that individual units now interact exactly like in a Curie-Weiss model of ferromagnets. So and this interaction will eventually give rise to the ordering and cooperative behavior. So it was already in this model, but you had to just consider controlled force rather than controlled displacement. Now, in fact, we'll look at, to see the robustness of these results, we'll also look at more general system where we make two small modifications. We replace hard spins to soft spins. So, because in fact, to match experiments, you have to have two different stiffnesses here, and also knowing that our filaments are in fact elastic, we'll add a kind of lump description of this elasticity by adding this spring that is, and in this case, energy is slightly modified, But it turns out that now we have this mean field interaction also in both in hard and soft device. So it's so adding this element is the important factor allowing to eliminate the degeneracy of the original Huxley model in a hard device. Still, of course, as we are going to see, we'll call this regularized Huxley-Simons model, while Huxley-Simons model will be already capturing the main effect. Okay, so we can look at zero temperature behavior. At zero temperature, or thermal if you want, the energy landscape of this. So what makes this material different from the usual material is that in usual material you would think some kind of series connection, while here you have a parallel connection. And this parallel connection is the origin of mean field interactions here that are not approximation as in Curie-Weiss, for instance, model or van der Waals theory, but here they're just reflection of the architecture of the organization of the units. So already this is a Huxley-Simons model, this is a regularized Huxley-Simons model. So this brings some additional complexity. Those are different metastable states. Here I think there may be 7 units. But what's interesting is that the global minimum of the energy already is not convex, as one would expect in normal material. Now in a soft device, this kind of so-called relaxed energy is concave. So we don't have these features as in a hard device. So it's strictly concave. Now, it's interesting to look at the barriers. So, because this is a beginning of understanding of why behavior in a soft device and hard device is different. So, what is happening in this point? So, up to here, all units were in one conformational state, and in this point, they switch to another conformational state. So, it happens here in this kind of brutal way. It also happens in a brutal way here. So since it happens in a brutal way, there is a barrier. So we want to, although the energy of the initial and the final state are the same, we want to assess the barrier for, say, in the AHS model and in the RHS model in a hard device and in a soft device. And that's what this picture shows. So we have to open some kind of additional internal variable that is natural here. It's a fraction of cross bridges in post-power stroke state. And when we go here in the soft device, we have a barrier, while here in the hard device, we don't have any barrier. Now in the regularized model, there is barriers in both cases, but in a soft device, it's much higher than in a hard device. So behind this will be this collective behavior, because in one case, you would have to turn simultaneously many units, while in a soft device, while in a hard device, collective effects are weaker. All right, so let's go to finite temperature. So here we just, in a Huxley-Simons model, and essentially they did it not directly, but computing equilibrium in their Kramer's scheme of reaction. You have to compute statistical sums. And the simplicity of the model, in fact, allows you to get analytical results here. So you can get formulas. But the important thing is that we expect a kind of ferromagnetic behavior in a soft device in a Huxley model. So that's what's happening at finite temperature. So the curves get a bit smoothed. So the zero temperature limit would be this dark solid curve, and then you increase the temperature as you get away from this curve. However, still with the finite temperature, you have the negative slope here at a finite temperature, and that's what Huxley was referring to. Although this is equilibrium computation based on direct computation of statistical sum, you are getting non-convex free energy in this case, and you are getting the negative slope. Here we see a finite size effect. So the solid curve is the thermodynamic limit, and for 300 particles units, we already see quite close agreement here also. Now, what's happening this is already equilibrium. So if we want to look at the fraction of units in one pre-power stroke and post-power stroke, here in a hard device we don't see cooperative behavior, so they all kind of randomly switch wells, while in the soft device the effective non-equilibrium or partially equilibrated Gibbs energy with respect to this internal parameter, order parameter, which is a fraction of units in one of the phases, we have a double well energy. And in fact, the behavior of the system is collective. So they all stay in one state and then switch to another state, but it happens collectively.
Now, what are these curves? I mean, are these from simulations, or are these?
Yeah, this is even from analytical formulas.
No, but I mean the P versus time curves.
Yeah, this is stochastic simulation from Langevin dynamics. Yes. So so you have those. You have a collective switch. So you have a kind of a microstructure in time. That's behind one of the points here. So the effective behavior along this curve is a certain force at a given displacement, but behind it there is a collective motion between the two states, while here there are no collective effects. Now, if you construct a phase diagram, so beta is 1 over T in the soft device for high temperatures, we have again the disordered phase, but for low temperature, the Gibbs free energy exhibits this double well structure. I'm saying that it's already equilibrium Gibbs energy at a given P, so it's not a behavior of individual unit. So it has this double well structure, and we have these two states, A and C, and what we see is actually oscillations, coherent oscillations between states A and C. So in magnets, we have a domain structure. So we have these oscillations, but these oscillations are in space. While here, since we don't have spatial dependence, it's all behaving in one point, we have collective oscillations in time. At a finite temperature, the regularized model shows basically similar behavior. And again, we are seeing consistently that the barriers in a hard device for, say, Helmholtz free energy are much smaller than the barriers for the Gibbs free energy. I didn't mention, we have a critical point here. So if we take the paper of Huxley, literally from 1971, and compute beta, beta is, of course, non-dimensional, so it's a temperature normalized by kind of elasticity, effective elasticity of the system, and the size of the power stroke. So it gets exactly into critical point. So as we are going to see, the more careful match of more recent parameters also keeps us quite close to this point. So this can be viewed, of course this diagram doesn't tell us that we should be in the point, but the data seem to be suggesting that the real muscles are operating very close to a critical point. We'll speculate a little bit about the origin of this. Okay. Yeah, so now the advantage of the regularized model that we have this additional variable, this kind of lump description of elasticity of the environment, which was not present in the Huxley model. So we can construct a phase diagram where the energy is bistable and where the free energy has a single minimum in the space of this elasticity and temperature. And so there is a nice analytical approximation here that because in fact the temperature is low, and so we are very close to the bottoms of the wells, and piecewise quadratic approximation allows us to get a nice analytical theory here. But at least experimental match that, based on all available data, places us very close to this critical point. Now, critical point is a line of critical points, of course. So the interesting thing that it suggests is that the system can be tuned into criticality by varying the effective elasticity of the environment, which is very similar to what Fred McIntosh was saying, that those networks can actively vary their effective stiffness in a very broad range. So it looks like they are close to this point. So we can speculate here. We looked at very simple system that was supposed to describe this system, but we want to speculate, of course, about this system. But we can say that the prototypical nature of Huxley-Simons models implies that passive collective behavior should be a property common to also general cross-linked acto-myosin networks, and the degree of cooperativity in such networks can be affected by elastic stiffness of the filaments. So generic system of this type may be then tuned to criticality by actively generated pre-stress. Now, of course, we don't know the direct mechanism, but at least we know that it seems like muscle system operating very close to criticality, so there must be some maybe active feedback that brings you to this state. Now, let's go back to the fact that kinetics is very slow in a hard device. And of course, we had some evidence that the barriers are drastically different, but we can also try to see it more directly. We can model the system instead of computing equilibrium properties by directly simulating stochastic dynamics with a thermal reservoir with a temperature T in hard and soft device. And this allows us to essentially reproduce those experiments. And in particular, the goal is to reach at the time scale of the experiment to reach the observed force and length recovery. Now, as we remember, what I said is that some equilibrium states could not be reached in a soft device. So there seemed to be some kinetic trapping here. And in fact, that's what we are seeing. So in a hard device, this type of stochastic modeling can allow you to reproduce equilibrium curves at the time scale of experiment, while in a soft device where collective behavior prevails, we are not reaching expected equilibrium state, but we are getting stuck in some other states, which one can call quasi-stationary state. And in fact, those are kind of a glassy states are known in systems with long-range interactions, the presence of this so-called Vlasov states, because Vlasov type of equations with the mean field interaction allow you to reach those states at a faster time scale, and then there is a much slower relaxation to Gibbs-Boltzmann type of equilibrium that we computed by dealing directly with statistical sums. So this system seemed to be, and that is the reason why in experiment people never see this range. It's called a gap in this muscle literature that you cannot reach by in experiment. They seem to be, the origin is this prevalence of this long-range interactions and this special architecture of these networks, because the fibers allow individual cross-linkers to communicate much more effective, more efficient than, say, in shape memory alloys, which would also have all these features, but they would not exhibit this type of kinetic trapping. And in fact, by using this regularized Huxley-Simmons model, Huxley-Simmons models already shows the difference between soft and hard device, but regularized Huxley-Simmons models allows you to match those data quite nicely. All right, so now let's try to build out of these units a material or a kind of a network. For instance, what we've been thinking about so far was the one single so-called half sarcomer. This unit that Huxley and Simmons modeled by n elements in parallel. Now, if we start putting, for instance, two half sarcomers together at 0 temperature, you start to see these non-affine states. Non-affine states, for instance, the two neighboring half sarcomers are not necessarily in the same states. And in fact, it is observed in this muscle system that those M lines are being often displaced of the expected positions, which is a kind of very trivial, elementary manifestation of non-affine behavior of the system that Fred was talking about in a much more general and fundamental setting. Now, here in the simple system, we see it in hard device, but we don't see it in a soft device. Again, there is a difference in behavior. So at finite temperature, we basically smoothen these curves, but this is maybe interesting. So if we try to use the mentality of our material and build out of these units whose constitutive behavior we know from those experiments, a material, we are in trouble. So the red curve is the behavior of the real system, and the black curve, this again for two half sarcomers, would be if we try to cook up this material out of behavior of individual elements. And again, we have difference in a micro level in a hard device and in a soft device. So we can combine in what in mechanics it's called Cauchy-Born type of reasoning, which means that we assume that we know constitutive behavior of the material point, and then we extend it to a continuum description. So here, this type of black curves would be if we take from microscale hard device behavior and try to extrapolate it into from 1 to 2 elements. And here, if we take soft device, again, at small scales, hard device and soft device are different. So you can get all kinds of behaviors here, which are not necessarily the one that real system shows, and this is a manifestation of non-affine structure of the real deformation, even in homogeneous loading. Now, if you make a chain of sarcomers, you of course converge to kind of convexification, and that's probably why in experiment Huxley didn't see the negative slope, because then you start having spatial inhomogeneity, not only temporal microstructure but also spatial microstructure that effectively averages out and makes this negative slope invisible. Now, in fact, it may be dangerous to view this system as just a series connection of half sarcomers. As you see, this is just an attempt to kind of unfold topology that's behind this network. There are different stages. You can rewrite it like this by keeping these M lines and Z disks, which is a passive cross-linkers. And then it would give you this type of topology. So you see that, and then even this is not a final result, because ultimately the system is anchored to the sarcolem, and the connections are really non-local, and parallel connections prevail. So that makes this system complex, even at the level of muscles. So so one has to be more careful in computing effective properties, even comparing to these chain computations that I've presented in the previous slide. Okay, now
2 minutes.
2 minutes. Okay. So I very briefly mention where is the power of the power stroke, because we have treated power stroke in a sense as a passive bistable element, but it's called power stroke, so there must be some power there. So here we have to turn to active processes, and the simplest representation of this active process would be to say, okay, we have this bistable element here. We didn't show the spring, but then it's connected to the actin, and it can move along the actin filament. Now experiments show, so here this is a fast time scales, but at longer time scales, system can generate a velocity, finite velocity at a given applied force. This is active process driven by ATP, and already almost 100 years ago it was understood that there is an antidissipative range where the system uses the energy of ATP to create a finite drift against the force. Now, how can we model it in our framework? Again, this is a Lim-Taylor cycle that was shown in the previous talk already. So we would like to design a mechanical system based on our ingredient, simple ingredient. This is still a toy model that would reproduce this cycle. So if we look at this toy picture that we've seen, the minimum number of degrees of freedom that we can identify is y and x. So in our previous study of passive system, x was kind of controlled, say it's a total length. But here, x also is a variable that lives in a periodic landscape. So for these two variables, we can write Langevin system. But here we'll also add a correlated component of noise, which will be given by periodic force. But now, since we want our power stroke to be active, we'll make a power stroke driven motor. So we'll make this force acting on the variable y minus x, which means that the variable that places inside the well, inside the it's a variable given allocation inside the double well potential. And we also take into consideration the fact that when power stroke happens, sterically the system may be closer or further away from the actin filament, just a steric effect. So our energy will have this structure. This is a periodic potential. This is a double well potential. And then there is this modulation that depends on the state of power stroke. In a post-power stroke, you are further away from the filament, and in the pre-power stroke, you are closer to the filament. So our function will have this structure. So this is a kind of a mixture of rocking and flashing ratchet. But it's important that ATP activity acts through the power stroke. And in this sense, it brings this model of non-processive motor very close to the model of processive motors, because that's how they work. They are driven by the conformational change between the two legs. Here it's a one-legged motor, kept, of course, by the fibers near actin filament, but working the same way. So we can study its drift properties. Maybe I'll mention one thing, that with this model we were not able to reproduce Lim-Taylor cycle, so we had to introduce a delay here, a delay in adjustment in the steric adjustment, so a hysteresis. Of Of course, hysteresis is an interesting thing. With hysteresis, it can drive the system even without without the correlated component in the noise. So we can get force-velocity relations, and this is what. Yeah, I'm out.
We're going to make it for
Okay, I'm going to. So we can reproduce. Yeah, we can reproduce Lim-Taylor cycle by pure mechanical elements, all 4 stages. So I can formulate conclusions. So the passive mechanical response of skeletal muscles at fast time scale is dominated by long-range interactions, which induce cooperative behavior without breaking the detailed balance. Now, this material is finely tuned to perform near marginal stability, which was emphasized in Fred McIntosh's talk, and which explains large fluctuations observed close to the stall force conditions in muscles. And finally, active muscle contraction can be driven by active power stroke element, which suggests that, in fact, processive and non-processive motors can operate by using the same mechanism. And of course, I didn't say enough about this last conclusion. Thank you.
Due to the imminent pressure of lunch, I'm going to cut off all questions and proceed to the next talk, which is by